Hello, myself is Kurangari from the Department of Electrical Engineering. I welcome you in a video lecture series of basic electrical engineering. We are discussing on work, power, and energy. So, work and energy. When work is done on an object, the object energy changes. Obviously, when we will do certain work on certain object, that the energy of that object always changes. So for example, when you push a shopping cart, your work goes into increasing the cart's kinetic energy, no doubt. When we push that cart, the kinetic means we are giving the energy to that cart, and that cart how increases that kinetic energy. When you climb a mountain, your work goes into increasing your potential energy. So as it goes up and up, our potential energy increases. So thus, kinetic energy is the energy of motion, while potential energy is the energy of position or condition. So that is the main difference between the kinetic and potential energy. When the kinetic energy is there, so the energy of motion is there, and potential energy is there, the energy of position is there, or energy of condition is there. At what position it belongs to. So remember this important point between the kinetic energy and the potential energy. Now work and energy, again in that, the Newton's law we have studied. So Newton's law and equations of motion may be used to derive a relationship between work and energy. In the figure below, it shows that a box is pushed by a person across an ice skating. Now he applies a certain force. F, let us say. Let's see how this force changes the box energy. No doubt, he pushes by applying a force equal to F in this direction. So that time, this box will get the energy, its kinetic energy changes. It gets its displacement will be there. It's pushed from this location to this location. So obviously, the energy of the box changes. The kinetic energy is the energy of motion. So we can use our knowledge of Newton's laws and the equation of motion to write a relationship between work and energy. Suppose you push a box of a mass m across an ice skating ring with a force F as shown in the previous figure, this figure. Okay, the mass of this box is m and you are pushing it on ice skating, applying the force equal to F. So the acceleration you will get as Newton's second law, it is F upon m, this force applied upon mass of the box. So as you learn, the speed and the displacement of an accelerating object are related by the equation of motion, that is v1 square is equal to vi square plus 2ad. So a slight rearranging, it gives 2ad is equal to f square minus vt vi square. So replacing a with f upon m, acceleration, and multiplying both sides by the equation m by 2, so it gives ft. A is equal to 1/2 m vf square minus 1/2 m vi square. So recalling from the previous lesson that work is W is equal to Fd, that we have seen. So W is equal to 1/2 mv f square minus 1/2 mvi square. So from this relationship, W is equal to 1/2 mv square minus 1/2 mvi square. So we see that the work done on the box or on any other object is related to the quantity, that is 1/2 mv square. So the quantity 1/2 mv square is defined as the kinetic energy of an object of mass m and speed v. The definition of kinetic energy, the kinetic energy is 1/2 mv square. So kinetic energy is always 1/2 mv square, and unit is meter square upon second square, that is the joule, meter per second square. So in general, the kinetic energy of an object is the energy due to its motion. Kinetic energy is measured with joule, the same unit used to measure the work. So the following table provides some examples of typical kinetic energies. A jet aircraft at 500 mph, so its approximate kinetic energy 10 to the power 9 joule. A car at 60 mph, its kinetic energy is 10 to the power 6. So like this, the house fly, its kinetic energy 10 to the power minus 3. Okay, so like this, the kinetic energy depends on its position. Now, the kinetic energy increases linearly with the mass and with the square of the velocity mv square. As the following example indicates, so here one example of what the kinetic energy is there. So 3,900 kg of truck is moving at 6 meter per second. So calculate its kinetic energy. And what is the truck's kinetic energy if its speed is doubled to 12 meter per second? So solution for this is substitute m is equal to 3900 kg and V is equal to 6 meter per second into equation of the kinetic energy 1 half mv square, and it gives the kinetic energy is 1 half mv square and it is 70,000 joules. Now in second part, what is the truck's kinetic energy if the speed of the truck increases double? So initially the speed is 6, now it will be 12. So you will get it is kinetic energy depends on the speed square. So therefore doubling the speed quadruples the kinetic energy, and the kinetic energy is equal to 4 times, that is 70,000, that is 2,80,000 joules. Now, as the equation W is equal to 1 half mvf square minus 1 half mvi square indicates the total work done on an object equals the change in its kinetic energy, this connection is known as the work energy theorem. So the work energy theorem, the total work is always change in the kinetic energy. So total work is only change in kinetic energy delta. Kinetic energy is 1 half mvf square minus 1 half mvi square. The following example shows how work is related to the change in kinetic energy. Now, what is the work if we change the kinetic energy? So, one example is here how much work is required for a 74 kg sprinter to accelerate from rest in zero position, zero speed to a speed of 2.2 meter per second. So, solution for this is since the initial speed is 0, so Vi is equal to 0. So, we have total kinetic work done is equal to delta Ke, kinetic energy is 1 half mvf square minus 1 half mvi square, but your initial speed is 0, so it is 1 half 74 kg into 2.2 meter per second bracket square minus 1 half 74 kg into 0 meter per second, means your total work done is 180 joule. So the sign of the work is related to the change in the kinetic energy. If the total work is positive, then the kinetic energy increases. If the total work is negative, the kinetic energy decreases. And if the total work is 0, then there is no change in the kinetic energy. It remains as it is. So the following example illustrates how the work energy theorem may be applied when an object has an initial speed. In previous example, the initial speed was 0, but now here there is a certain initial speed, and in such a case, how the work energy theorem works on it. So here a boy does 19 joule of work as he pulls a 6.4 kg sled through a distance of 2 meters. He is pulling this sled. Initially, the boy is at 19 joule. He pulls 6.4 kg sled through a distance of 2 meters. No other work is done on the sled. If the initial speed of the sled is 0.5 meter per second, so what is its final speed? And final speed हमें निकालना है. Total work उसने 19 जूल किया है, तो हमें total work पता है. Okay, initial velocity हमें पता है. Okay, so you can easily find out the final. So the rearranging the work energy theorem to solve for the final kinetic energy 1 half mvf square is equal to this. Vf हमें निकालना है. So 1 half mvf square is equal to total work plus 1 half mvi square. So Vi is equal to, sorry, Vi minus under root of 2 total work upon m minus vi square. So solving this, you will get the final velocity vi as 2.5 meter per second. Now here, consider this work is done on a lifting a ball. How much work is done? So as the figure below indicates, work must be done to lift a ball from the floor onto a shelf. So even though the ball has no kinetic energy, once it is resting on the shelf, the work done in lifting the ball is not lost. So it is stored as potential energy, no doubt. So when you release it, so that time it comes or fall down with a certain potential, certain kinetic energy. Means initially it stored the potential energy because its position was changed. This is for today. Next I will discuss the next topic. Thank you very much.